All right, everyone. Hello, hello. This is Volts for June 24th, 2026. How to keep people cool without making the planet even hotter. I'm your host, David Roberts. Today, keeping ourselves and our products cool, air conditioning and refrigeration, basically, produces around 7% of global greenhouse gas emissions, as much as global cement production. If the technology doesn't substantially improve and growth continues, especially in emerging economies where air conditioning ownership is climbing 10 to 15% a year, that share could nearly double by 2050. The International Energy Agency now projects air conditioning electricity demand will grow faster than data center demand between now and 2030. Cooling heats the climate in two ways. First, the refrigerants leaking out of air conditioners are powerful greenhouse gases, often thousands of times more potent than CO2. Second, the electricity to run them is already 17% of global power consumption, projected to triple by 2050, and a lamentable amount of that power still comes from fossil fuels. In short, more cooling produces more warming, which raises demand for cooling, which produces more warming, and so on. It is a bit of a doom loop. Unlike many subjects we cover here on Volts, this is not primarily a tech innovation problem. Between more efficient air conditioners and electricity decarbonization, we already have the technology to cut cooling emissions by something like 97%. No substantial tech breakthroughs required. The trick is that getting there means a broad array of reforms. Everything from rewriting how we test air conditioners, to retooling manufacturing, to upgrading buildings, to redesigning cities. It's a lot. To walk through it with me, I'm talking today with Ankit Kalanki, who leads RMI's global cooling initiatives. We are going to get into all of it. Why current air conditioners are underperforming, what reforms could boost efficiency, new tech on the horizon, and the building and urban design pieces that must be part of the answer. I've been meaning to get to this subject for a long, long time, so I am super excited to jump into it. All right then, Ankit Kalanki, welcome to Volts. Thank you so much for coming.
Thank you, Dave. It's a pleasure.
All right, we've got so much ground to cover here. I'm somewhat daunted, but I think the right place to start is just a very quick walkthrough of basic air conditioning technology. I was sort of blown away as I was reading the history of this. So this guy, Willis Carrier, people will recognize that name, continues to be an air conditioning company to this day. Willis Carrier patented this basic vapor compression process in 1902. And the pieces of it have changed somewhat since then, but the basic architecture of how it works is still basically the same. We're still using vapor compression technology. So maybe just start by walking briefly through what is vapor compression technology? How does it work? How do we cool spaces with this today?
So vapor compression technology works by moving heat from indoor spaces to outdoor spaces. That's the fundamental of what cooling or air conditioning really is and what an air conditioner does. It's not about making cold, but it's about moving the heat.
Right.
So air conditioner, think about it as a heat pump where you are moving heat from inside the rooms and you are dumping it outside. The working fluid that enables this is what we call as a refrigerant. That refrigerant takes the heat from indoor spaces, it evaporates, it absorbs that heat, then you have a technology called compressor, where that refrigerant gas gets compressed. And then you have the outdoor unit where that heat goes and gets rejected to the outdoor ambient. And the cycle gets repeated. And it's a closed loop cycle. So that's how the vapor compression technology works. And that's how the air conditioner moves heat outside and keeps your indoor spaces cool.
Right. And that's air conditioning of spaces for people. That's refrigeration of, coolers. That's basically all cooling works basically like
Yes.
that. You take the refrigerant, it evaporates and absorbs heat, then you compress it, makes it super hot, goes outside, and it condenses, which releases the heat. Then you reduce the pressure again, it goes back inside, does it all over again. And this, like I said, is basically the same. Like these pieces, refrigerants have changed, compressors have changed somewhat and gotten more efficient, and so on and so forth. But that basic cycle is still how air conditioners work today. And as you mentioned, I mean, we're not going to get into this, but just as a side thing for my listeners, I've done many podcasts on heat pumps. And this is exactly the same way a heat pump works, just in reverse. A heat pump is just a reverse air conditioner, or an air conditioner is just a reverse heat pump, I guess you could say. So let's then talk about the basic levers we can use to improve this process. These pieces, the refrigerant, the compressor, etc. How do you improve these pieces? Well, maybe we'll just start with refrigerants, because the history of refrigerants is quite interesting. There's been a lot of rounds of angst and replacement, and then more angst and more replacement. So tell us a little bit about how refrigerants have evolved.
Yeah, you said it right. It's like a closed loop with refrigerants where we are, the full circle is getting completed again. When we first used any form of cooling or mechanical cooling, it was based on natural refrigerants. Carbon dioxide, ammonia were used as refrigerants very early when we wanted cooling and refrigeration. Then we evolved to synthetic refrigerants, which were called as chlorofluorocarbons, because they were more efficient in doing the same thing or providing cooling and refrigeration. But while doing so, they were causing a very big problem, which is a hole in the ozone layer. And because of that, you had Montreal Protocol treaty that decided to phase down and ultimately phase out all these chlorofluorocarbon refrigerant gases. And that made way to hydrofluorochlorocarbons, which we call as HFCs, that are widely used today, that were introduced because they had zero ozone depleting potential, or ODP.
Right.
And that was a way at that time for solving the problem of the hole in the ozone layer. But as these HFCs became more and more common and widely adopted, we all realized that, oh, these are now very high potent greenhouse gases that have, on an average, 2,000 times more global warming potential than carbon dioxide. And so if they get released into the environment, it could be a climate catastrophe.
Right. And just to insert here, they're not released into the environment from an air conditioner that's working properly. They leak in the manufacturing, transport, units that aren't working correctly. These are all leaks we're talking about, but there are hundreds of millions of these units around. And so all these small leaks of highly, highly potent greenhouse gases really add up.
Precisely. I like to say that refrigerant inside a closed system is totally fine as long as it doesn't leak.
Right.
Because it's giving you the cooling that you need and the refrigeration that you need. And it's allowing you to do it in a very efficient way. But it's through that operating lifetime, when the system gets serviced by a contractor that comes to your place, and then they kind of play with the system. And over a period of time, due to the corrosive nature of the environment or other ambient fake factors, the system might develop some issues, like coil gets corroded, and then you have some leaks in the system.
And disposal too, right?
Yes, exactly. I was going to come to that end of life is another problem, where despite in the United States, for example, refrigerant venting is legally banned. There is very limited amount of refrigerant recovery that actually happens at the end of life. And so you end up in a system or in a loop where a lot of that refrigerant ends up getting leaked into the environment at the end of life as well, which is the problem.
So now, though, we're trying to move past HFCs too.
Yes. Exactly. So now that the world has discovered and understood that the HFCs are also very highly potent greenhouse gases, and it's actually contributing to global warming significantly because they're also short lived and they are significantly more potent. Now we are going back to natural refrigerants in many parts of the world. We are looking at hydrocarbons, which is one of the refrigerant is propane, which is being used for air conditioning applications, which has a global warming potential of about 3. In industrial applications, ammonia continues to be a refrigerant of choice for many. In grocery stores, in many industrial applications, carbon dioxide with a GWP of 1 is increasingly also getting adopted. So we are kind of heading towards where it all started,
Yeah,
the
full
world of
circle.
natural refrigerants.
But like the reason we moved off those natural refrigerants in the first place is like ammonia is quite toxic, propane is quite flammable. Like there were trade-offs with these that led us away from them in the first place. Like those are still problems, right? We've not yet found a refrigerant that is sort of the magic, does all the things we want with none of the things we don't want, right? I mean, we're now returning to some that are toxic and or flammable. And
Yes, we have not found any ideal refrigerant, if you will, to date that checks all our boxes. But I will say, depending on the application, you can make what refrigerant works best. So if it's an environment where you have outdoor setups and you have a large, access to ambience, you can consider some of these natural refrigerants, which have been used in many industrial applications for many, many decades now. So it's more about getting used to it with the right set of safety practices and adapting it and adopting it at scale.
so let's also talk briefly about the other pieces then. Compressors, these are driven by electric motors. And I guess all Volts listeners know electric motors have gotten more efficient over time. How have compressors improved?
So compressor, as everyone calls it, it's the heart of the air conditioner or a heat pump technology. That's what makes the air conditioner deliver the cooling or the heating.
And that's what's consuming the electricity. Like everything else is basically plumbing.
Yes, I mean that's the majority of the power. The compressor dictates how much power, and more particularly peak demand, will air conditioning and heat pump contribute. So you're right. The industry on the compressor technology has evolved significantly over the last few decades. We used to have a lot of fixed speed compressor technology, which means basically that it's only either on or either off. So once you set a certain temperature on your thermostat or using a remote control on your air conditioner, your system will operate until it reaches that set point, and then your technology will cut off. And it was a technology that was commonly used for multiple decades. Over the last, I will say, decade or so, markets have evolved to what we call as inverter technology, or in another terms, it's also called as variable speed technology, where now you are not kind of in the on and off situation only, but the compressor reduces its speed as you reach closer to your set point or the point that you have set on the threshold. And there has been this innovation where you have this variable frequency drive or VFD that gets attached to your compressor and compressor motor technology. And it enables that adjustment of the speed based on how quickly and how much cooling or heating you want from the system. So when you look at that transition, and if I give you example, in India, for example, the fixed speed market was almost 80% in 2015. And in 2025, it's the opposite.
Oh, interesting.
80% market is now inverter technology in the residential air conditioning sector. Japan is primarily inverter technology. China is again very high on inverter technology, close to 80-90% as well. So most of the market has evolved and moved on to inverter technology, and now that's an area where now more innovation is needed as to how you can further improve the aspects of the variable speed technology.
Right. And then the other pieces, I guess heat exchangers have probably improved over time. Also, and the controls. We'll talk a little bit about the sort of software controls, because as I understand it, that's also kind of a big piece of this.
That is, in my view, today's biggest piece that needs to get solved for, that will significantly improve the efficiency of air conditioners. And it is tied to two pieces. One is what we need air conditioners for in real terms. And controls has a big role to play in that. And controls has a big role to play in how these air conditioners are tested and rated. And so controls is like the piece that connects both of them. And I'll come to the first part first. And you mentioned about Willis Carrier and the history of air conditioning. Let me just kind of share this with the audience, that air conditioner technology in the first place was not invented to provide cold temperatures. It was actually meant to reduce humidity or remove the moisture from the air, because where Willis Carrier was working back in the day, in a Brooklyn based paper factory, and he was constantly noticing the warping of the paper, and it was really disrupting the quality of the paper. And that's where the idea kind of came from, that what can we do to remove moisture from the air so that the paper quality doesn't get affected. And now, over many many years, that definition had changed. It became about how quickly you can cool the air and how quickly you can reduce the temperature. But again, with the climate change and with the global warming and the pace at which it's happening, you are seeing very humid conditions that people are experiencing all around the world. And now it's again kind of going back to how air conditioners can deliver not just lower temperatures, but also reduce humidity and reduce moisture from the air and deliver comfort in the true sense, and do that in a very energy efficient manner, and in a way that's affordable for people to operate it. So controls are a very critical element, where they can make the air conditioner smarter in how they assess temperature and humidity, and how they optimize this compressor and this refrigerant flow and the fan speed, and how all of that comes together to deliver the comfort that people actually need. So controls has a very big role to play there.
The one other thing that's probably worth mentioning, just in terms of the AC units themselves, is I presume we could get better at reducing these leaks, right? I mean, I guess that's just more regulations, better training of technicians, better disposal techniques. I mean, is there work underway to just kind of reduce the amount of leakage over the course of the lifespan?
Absolutely. Installing leak detection systems is one intervention where a lot of work is happening, and especially in the commercial sectors where you have several thousands of pounds of refrigerant inside a facility.
Yeah.
Installing these leak detection systems is a way to assess those leaks as soon as they happen, and then bringing your contractor on site to kind of fix that. And then at the end of life, there is a lot of attention being given to how do we ensure and incentivize contractors and technicians to recover the refrigerant at the end of life and not letting it vent, and what are the right practices around it. So definitely a lot of effort is going on, and a lot of awareness is being built within the industry, within the communities, to stop those leaks in the first place and at the end of life as well.
Right. So if you put together, I mean, this is the interesting thing to me. If you put together all the things that we already know how to do, like RMI has this global cooling prize, and prototypes that have won those prizes have been 60 to 75% lower electricity use than typical ACs, just using technologies that we already have. So then the question is, why can't a US consumer walk into a Home Depot and buy one of these super efficient ACs? And oddly, the answer to that question sort of traces back to how they are tested and rated. So, and this is the focus of a lot of your work. So, talk us through briefly what's wrong with how we test and rate these things today.
Yeah, I think that's the crux of the problem, that if they are technically feasible, then why are they not commercialized?
Right.
And that's where, the commercialization journey is very different from an innovation journey.
Yes.
Where you develop prototypes, great, you have proven something, but then commercialization journey is a long journey. There are iterations on the prototypes. You are looking at different standards for safety and for compliance, and depending on the market they can vary. And then you have to understand the market and what their needs are. And so that journey is where we are, actively spending a lot of time on, as you mentioned, through the Global Cooling Efficiency Accelerator. And standards is one piece, Dave, which is extremely crucial in this commercialization journey. Industry designs products to standards, and those standards get referenced everywhere, whether you're looking at a building code, and when they specify equipment and the performance, it all ties back to what standard is used to rate and assess the performance of those air conditioner technologies. And it's not there is nothing wrong. I don't blame industry there, because industry is designing to standards. They have done a very good job at making sure that products are compliant, and then they have been cost optimized to make air conditioners affordable for many, many millions of people around the world. So where the change needs to happen is really how, in the first place, those ACs are rated and tested, because then industry will do it once the standards change.
Right. And this comes down to the difference between latent cooling and sensible cooling.
Yes.
Tell us briefly, like, what those mean.
Yeah. Sensible cooling means, basically, in simple terms, temperature based cooling. If you have to go down from 80 to 70 degree Fahrenheit, how quickly and how efficiently your air conditioner can deliver that cooling, that's sensible cooling. Now, if you have a space where you are feeling very humid, because relative humidity is 85%, and you want to bring it down to 60%, all that effort that will go into reducing the moisture, that's the latent cooling part. And you expect air conditioner to do both of them at the same time. How it happens today is you use temperature as a proxy for managing humidity, because air conditioners only have a temperature sensor inside them.
Right.
And so you start with a certain temperature set point on your thermostat, and when you still feel sticky, or you walk into a conference room and it's feeling cold but it's clammy and it's muggy, you will keep reducing your thermostat until you feel the relatively drier air. And so the air conditioner is doing that.
Right. This is crucial, that even cooler air, if it's still humid,
Yes.
is not comfortable. And people tend to crank the temperature down further if that happens.
And that wastes energy today. And that's the piece that standards can solve for. So standards today, based on which the air conditioners are designed and tested and rated for performance, they use temperature as a way to assess the efficiency. And that's what goes on the labels that you see on air conditioners today. So it's purely sensible cooling based approach of testing today. And humidity management is a byproduct, because when you cool the air, there is some level of moisture, that gets removed when as air reaches its dew point temperature. However, if we have to really deliver better cooling, if we have to really deliver cooling that provides comfort to people and does not waste energy and does that in an energy efficient manner, we have to start thinking about how can we bring latent cooling not as a byproduct but as a central piece of that testing protocol and the testing method against which air conditioners are designed. And that's the kind of effort that RMI, along with partners, are actively working towards, as to how do we build, on one side, the awareness that this is missing today, and then generating the data and the evidence through field testing that we have done and through engaging with manufacturers, to then go to the standard setting bodies and say that we need to change these standards, because that's the only way we can avoid locking inefficiencies for multiple decades to come, especially when you look at the boom in air conditioning in global south countries.
Right. You've done these field tests that show that when it's humid, air conditioners are using up to 30% more energy than you would think from their ratings, right? From their standards ratings, because people are pushing them down farther than what the temperature would suggest. And so currently they're wasting a ton of that energy just because that humidity piece is not getting measured. So, reading around about this, it sounds like you are making progress on this. The incoming president of ASHRAE, I'm not even going to attempt to unpack that acronym, but it's basically the Association of Heating and Cooling Engineers. He sounds like he's heard about these field tests and he's cognizant of the problem. The ISO, everybody knows that it's sort of international standards organization. It sounds like they're working on a new standard, and like India's Bureau of Energy Efficiency has updated some of its benchmarks. So it does sound like things are moving. So I wonder where that process is and how long, what is the distance between what's currently happening and that bright future when I can walk into a Home Depot and see a standard rating that accurately reflects these things.
You're absolutely right. There has been a lot of good progress and in the right direction in regards to the standards conversation. The ASHRAE president highlighting the overcooling issue and the energy waste associated with overcooling in his presidential speech globally, that he travels and addresses the technical community and the engineers. That has really elevated the awareness around it. And those same people then go into the technical meetings and then talk about it. So that definitely has helped us kind of raise the awareness around it. ISO is already working on a new standard, which is again a move in the right direction where it's going to shift away from a traditional standard capacity based approach to an approach which recognizes better controls. And with that controls, you can optimize the performance of your air conditioners. And ISO is heading in that direction. And we are hopeful that in the next couple of years, ISO will come out with a fully published standard along that updated standard process. And then it will come down to the countries. So once ISO publishes a certain standard, then the national standard bodies in India, it's the Bureau of Indian Standards. In the US, it could be the DOE or the AHRI. Then they will look at that, or they will already start working on it in parallel and think about how can we better acknowledge the aspects of that standard into the national standards, because every manufacturer will design the products that are sold in the market according to the national standards and the regulations. And so that process takes its own time, because there is a lot of consensus building, and that needs to happen through the technical committee efforts. However, this is where organizations like RMI again step in, where industry players, we find the players that are really trying to kind of take the first step and are seeing this change and acknowledge that this will happen. It's not about if, it's about like when and how soon it will happen. And so they're noticing it, and they are willing to kind of take that first step. And then we work with them, and we work with aspirational buyers and actors on the demand side who are willing to take that step in regards to demonstrating and deploying those technologies that can generate the market confidence that policymakers need to see ultimately to expedite their efforts on the standards front as well. So it's like they are all interconnected. It's not like a sequential process. And so we have to work on all of those aspects where, when one industry player jumps in, then it creates a FOMO. And then other industry players also jump in. And then when they see one buyer doing it, there are others who also want to do it. And so then you kind of start creating that multiple voices around it. And that's how kind of you start shaping the market. And ultimately that kind of leads to the day when we walk into a store and we see a product that is optimized for humidity, that is optimized for delivering comfort while delivering energy efficiency in the real world and not just on a label.
Well, there's also a sort of set of problems like if a new standard drops, manufacturers, OEMs, still need the tools by which to meet those standards. And those aren't necessarily in place now. Is there work sort of starting to build those up in advance? Like they need their own testing infrastructure, they need their own sort of modeling tools that are optimized to this kind of thing. How long before, like, I don't know, some mid-tier OEM in, I don't know, Vietnam, is capable of producing these, even if there is a new standard in place?
Yeah. And that's an important question because that's what dictates the timeline for adoption at the national level, Dave. The readiness of the local labs and the local manufacturers, testing capabilities, and that is what determines how soon and to what extent those standards will get adopted. And there are efforts that are happening where RMI, for instance, is engaged in inter-laboratory testing, where we are looking at the different test protocols that exist that are different from what is followed today as an industry practice. And we are trying to work with those research institutions and those labs in different regions to help everyone come on the same page by better showing that these new test methods are replicable, they produce consistent results. Whether you do it in Japan, whether you do it in India, whether you do it in the US, you are expecting to see consistent results. And those are the kind of efforts that allow test labs and industry players to build the confidence that yes, that evidence kind of helps build their confidence further, which then kind of moves us to the next phase of building the consensus and moving to the adoption of the standards as well.
If you were pushed to guess at some sort of timeline, how long is this going to take to get these? Like, as we say, like, we're capable with this current technology we have of getting whatever 60 70% better. How long do you think before those 60 to 70% better air conditioners are in stores in, say, emerging economies? Do you have any sort of like guess as to that timeline? Hey there, everybody. Don't worry, I'm not going to tell you about a new mattress or push a credit card on you. This isn't an ad. There are no ads on Volts. It is supported entirely by listeners like you. If you'll indulge me for a second, I'd like to ask for your support. I started Volts because we're all surrounded by depressing news about climate change and misinformation about clean energy, and it's never been more important to share the stories of the real people on the ground doing the real work of transition and all the ingenuity and courage and public spirit they are bringing to it. People are hungry to hear these stories, to learn from and find inspiration in them. I've heard from people who changed majors or careers after hearing episodes of Volts. People using it in classrooms and community groups, even state legislators who have passed bills inspired by specific episodes. Sharing these stories matters. It makes a difference. If you have found value in it and want to help me continue doing it, I hope you will join the community of paid subscribers at volts.wtf. It's about the cost of a cup of coffee a month. If you don't like subscriptions, you can make a one-time contribution, leave a review on Apple or Spotify, or just tell a friend about Volts. I am grateful for any and all support. If you're already a paid subscriber, thank you. And now, back to the show. How long do you think before those 60 to 70% better air conditioners are in stores in, say, emerging economies? Do you have any sort of like guess as to that timeline?
I will answer this question in a slightly different way, if I can. We know what and how we can reach that 60 to 70% target of super efficient ACs. And how we go about that journey is we start with what is the most practical and the most feasible way to introduce products in the market that have controls capabilities that are making these air conditioners smarter in delivering comfort in the real world.
Mm-hmm.
And you can do that with existing set of compressors, with existing set of heat exchangers, what exists today, because supply chain readiness is also important when you think about emerging economies and where they are and the policy ecosystem there. So knowing what exists today and what manufacturers are able to do today, taking that first step of advancing controls by making your air conditioner better respond to both temperature and humidity can instantly deliver 15 to 20% savings right off the bat. And that I will say that I feel confident that that could happen in a matter of a couple of years timeline.
Mm-hmm.
Because you are not looking at establishing a new supply chain or finding a new vendor. You can work with your existing vendors and you can do that. And from there on, the journey really goes on to advancing towards that 60 to 70% number, where controls is part of that. But now you have to think about compressor technology, and you have to think about heat exchanger technology, and what exists today and where is the innovation happening,
And the regulatory updates, the standards updates.
regulatory updates. And yes, and manufacturers are in a very tricky business. I mean, if I have to kind of spend 1 minute on this, air conditioning industry is not a very profit making industry. The margins are very tight, and they rely on commodities, copper, aluminum, plastic. That's kind of the core of what makes an air conditioner today. And so when you are thinking about, on one hand, industry is being asked to constantly raise the efficiency benchmarks and the efficiency of their products, while keeping the products affordable, while keeping the supply chain domestic, all of that, it's a very complicated and a very complex problem and a multivariable problem to solve for. And so this is why I think like a phased approach is something that we can really make good progress with, where these updated products that have existing hardware and use controls, better controls, can immediately bring savings to people, to the power grids, to the environment. And from there on, we can continue to go towards that ceiling, and ultimately achieve that 60-70% target.
Okay, let's pull the lens back a little bit from the AC units themselves. Let's talk about, for a minute, the buildings that these AC units are in. There's lots you can do with buildings to reduce how much cooling you need in it. Maybe can you just like mention a few of those things?
Absolutely. I mean, I like to say or think about it as, you don't need air conditioning in the first place. Start with thinking about your building and how can you reduce the cooling need inside the building by measures like shades and ventilation and insulation, windows, better insulating windows. Paint your roofs with materials that can reflect and radiate the heat into the outer space. All of that can have a significant impact on the amount of heat that gets trapped inside the buildings, that ultimately gets radiated through the walls and through people. And once you do that, then your heat load that actually has to be removed to outdoor, that we talked about in the very beginning, is significantly reduced. And so you can now reduce your size of the air conditioner, or in some cases, maybe you don't even need an air conditioner, depending on where in the world you are. So it's very important.
And then, of course, you're getting into building codes, construction codes, all that kind of stuff. Obviously, that's a whole rabbit hole we could go down. But one thing I did kind of want to just take a brief look at, just because I'm kind of fascinated by it. I should probably do a separate pod on this, but talk briefly about these passive daytime radiative cooling materials. So everybody, I think, is familiar with painting roofs white, right? I mean, that reflects a lot of heat away. That alone can do a lot. But then they have these special new paints, these special new materials. Just say a word briefly about these things, because they kind of seem like magic to me.
It is fascinating, PDRC, or passive daytime radiative cooling products, which can take many forms. Paint is one form, which they can take. And the interesting thing about them is that they reflect the heat like a typical white paint would, much more efficiently, but they also radiate the heat. So the infrared portion of the sunlight, which is really what is the heat component,
Mm-hmm.
and also from the indoors, these PDRC materials can actually transfer all of that heat to the outer space in a very narrow window.
Right, it goes right through the atmosphere.
Yes. And there's a very narrow window, when you think about the science behind it, there's a very narrow window in the atmosphere of 8 nanometers to 15 nanometers, between which you have to produce that radiation, or that reflection, for it to pass to that outer space. And these PDRC materials have been tuned in a way and have been innovated in a way where they enable that heat to go into that outer space through that narrow window. And that's the beauty of it, where you can then achieve significant reduction not just on the surface of the roof, but also indoors because it's able to radiate the heat also from the roof.
Right. You can actually, it could help your building be below ambient temperature.
Yes.
It could actively cool the building. It's just wild to me. And really, when you think about it, it's not just reflecting the sunlight away, it's sending heat out into the atmosphere. So, in some tiny way, it's helping with global warming too, in a very marginal way, but absolutely fascinating. So, just on white roofs, I constantly have people ask me whenever this comes up, and I've had the question myself, which is that just seems so obvious and easy. Like they've done studies where if you paint a bunch of roofs white in an urban area, you can reduce this urban heat island effect that you have where heat concentrates in urban areas. You can keep buildings cooler, and white paint is not expensive. So I just kind of wonder, why isn't there more of that? Like, why isn't that the default? Why haven't we seen that spread faster and become more ubiquitous? Do you have any theories on that?
So there are some what we like to call as practical aspects of why the scaling has not happened at the pace at which we would like it to be. Again, in this, similar to air conditioner, technology is not the problem. It's the other elements of it when you think about commercialization and deployment that have to be considered as well. So a couple of things that are important to note which impact the adoption at scale is, one is that the reflection itself and the glare that comes from just painting everything white. And so that has been raised as a potential concern, and so there are efforts to solve for that, but that's one of the concerns, that if you paint everything white, the glare becomes like a concern and an issue for people that are in the surrounding areas or in the surrounding buildings. The second is, depending on where you are in dense urban environments where you have tall buildings, skyscrapers, all that reflected heat might just bounce between the different buildings and it might just remain trapped. So it is reflecting from one roof, but then it might get reflected back through other surfaces. And so it's not a solution that can be just applied anywhere, but it context specific. Yes, it can definitely be applied and needs to be applied. The third more practical thing is the wear and tear. When it rains, if you live in an area where there is a lot of debris or dust, the effectiveness of that traditional white paint also gets impacted. And so there are more efforts needed to solve for some of those practical aspects of the work. So yes, while they are great in reflecting the sunlight, and in studies, we have seen the numbers in terms of how much delta on the temperature standpoint they can get. But when it comes from a durability standpoint, I think there is more work needed for them to get really adopted at scale.
And the PDRCs, these sort of magic materials that reflect the infrared out into space, are they commercial at any scale yet?
There is a lot of active testing happening of PDRC materials in different forms, as a film on solar panels, as a paint. So there are a lot of startups, including organizations like RMI, that are supporting these startups to test the veracity of the claims of some of these PDRC products to generate more evidence and generate more awareness. So that's where we are at this point, and we need to do a lot of evidence generation around not just these technical and performance aspects, but also on some of these durability aspects, so that they can really build that confidence among the policymakers and amongst the adopters in different parts of the world.
Interesting. Okay, and now briefly, let's pull the lens back even farther from the building to the city, to urban design. There are also things that city planners can do, again, to provide comfort, because that is ultimately what we're about, right? Comfort. Talk about a few of the things you can do at kind of the neighborhood and city level to help cool people.
Yeah, so I think this work that happens at the city level and urban level is a key part of building resilience, is what I like to call it, because whatever we talked about until now, everything is inside the buildings or impacts people inside the buildings.
Right.
But then you have people that are working outdoors. And so urban level measures and urban heat mitigation measures are extremely crucial if we are to truly address the need for cooling and tackle this heat issue for people around the world. So some of the ways in which urban heat mitigation happens is, you think about greening the spaces, planting more trees. There are
Trees.
efforts happening around that, and a lot of policies at the local level, at the municipal level, are encouraging green spaces for people. Establishing cooling centers is another way where outdoor workers can go to these spaces that have some form of a cooling mechanism, whether it's fans or evaporative or mist based cooling or air conditioning, where they can get some respite having worked outdoors. And I will say the most fundamental part of this is, when you think about urban heat, is how can we inform people in a timely manner so that they can take the appropriate action. And multiple, again, cities do this in many different ways. You have warning systems and announcements that happen, and more of that is now becoming a priority for local administrations, where they are increasingly using the technology and using the weather data to really inform people about these heat issues in advance, so that they can either plan their work properly or they can take breaks accordingly, so that they don't cross a threshold which might impact productivity, and in some cases maybe even become fatal, given the extent of the heat.
A couple other specific questions about this. One of the things that occurred to me is just like every city, everywhere basically, has tons of pavement, roads basically, roads and parking lots, and pavement is, of course, black or very dark. So it absorbs heat, and everybody's familiar. Anybody who's been to Phoenix, Arizona, or anywhere, knows that like the pavement itself can become hot enough to genuinely be painful. And is there any way to make lighter colored pavement? Is that a thing?
It is a thing, and we RMI has tested that in India, in Palava city, in near Mumbai, and we have seen between 3 and 5 degrees Celsius of temperature change with light colored tiles and reflective blocks. So it is a thing, and it exists, and we have tested them in India as well.
And one other piece, which is fascinating to me, is just district cooling. Of course, Volts listeners, I think, are very familiar or should be with district heating, where you just make heat centrally and then pipe it to buildings. But there's also district cooling, where you're doing this sort of, kind of vapor compression, that whole same cycle, but on a kind of larger, more industrial scale, and then piping the air. Is that common? Is it spreading? Is that a big piece of the puzzle here?
It is an important piece of the overall solution set. There is no one size fits all solution when it comes
Sure.
to how you provide better cooling to people, and it's so context dependent. So, district cooling definitely is one piece of that broad, big puzzle on how you provide access to cooling to people, especially if you think about mixed mode developments, where you have a good mix of residential, commercial, industrial office spaces, where the cooling load is fairly consistent on an average.
Hmm.
Those kind of setups, those kind of parks, which are coming up in many developing countries, and if I think district cooling is a very good solution for those kind of setups. In traditional dense urban environments, is obviously hard to have all that centralized system and piping and delivering cooling.
Right, especially if you're trying to retrofit
Correct.
already built environments.
Correct. But in these new projects that are coming up, and if you can plan them properly, and if you can have a cooling load that is averaged in a way where you can meet everyone's demand, district cooling can offer a very, very good opportunity to reduce the cost for consumers. Because then you can think about it as the project developer will be very much incentivized to invest in the most efficient solution instead of a low efficiency product, because they will be getting paid by how much amount of cooling they deliver. And the more efficient they are, the more efficient they are with their systems, the maintenance of their systems, the more incentive they have, and the more from a business standpoint, the more profitable it is. So could be a win-win for people, where consumers don't have to own the asset, they don't have to worry about the upfront cost, they don't just have to pay for the cooling they use, and the developer and the operator is incentivized to invest in the most efficient system and better maintenance, because that way they can improve their financing position as well. And so in that way, I think district cooling has definitely a potential, but it's context dependent, like I started with.
Sure, sure. Okay, so we don't have a ton of time left, but there's a whole, I mean, again, here we come to a thing we could do a whole pod on, which is most of what we have talked about, and I think most current efforts, and I think most of kind of your hopes for the near and midterm future are around improving the basic vapor compression, systems as they exist today, making them work better. But there are under development here and there among startups and labs and such, there are some kind of fundamental alternatives
Yes.
emerging. And I thought maybe we could just like run through a few of those quickly. Maybe we could start with desiccants, because those I think are maybe the closest and maybe are even being integrated into kind of vapor compression. So talk a little bit about that first.
Yeah, and it again comes back to humidity, where we started with. Desiccants are a solution to manage that humidity in an effective way. And we are seeing a lot of innovation from the startups, and multiple of them are also supported by RMI through our third derivative program. They have kind of developed desiccant materials and innovation in that desiccant material space, where they integrate or attach onto an existing vapor compression system, and they can independently and separately manage the sensible cooling or the temperature, and latent cooling or the humidity. And that way, now your air conditioner doesn't have to overcool the air to remove the moisture. Now the desiccant takes care of that humidity and the moisture removal. It sucks the moisture out of the air, makes the air dry, and your vapor compression system is only doing just enough to reach the temperature that you feel comfortable at. And so that's one area of innovation which has a lot of potential and a lot of startup activity.
And desiccants are just materials that absorb moisture, right? More or less.
Correct. But they can be in liquid form and solid form. So there are varieties of it. But yes, fundamentally, they are the ones that these materials suck the moisture out of the air.
So you suck the moisture out, and then the dry air goes into the traditional vapor compression system, but it has to do less work.
Correct. The innovation piece in the desiccant solution set is, how do you regenerate that desiccant? That's the piece which often gets missed. So while you are solving one problem, you don't want to create another problem where you are now spending energy to regenerate that desiccant, because that desiccant material, like any other moisture absorbing or water absorbing material, will get saturated as it absorbs more and more moisture. And so, how effectively and efficiently can you regenerate that desiccant so that it's ready to work efficiently?
When you say regenerate, are you squeezing the moisture back out of it, or are you replacing it with new desiccant?
Squeezing the moisture back out of it. So you need typically some kind of a heat source to do that process. And how efficiently and innovatively you do that is what will determine the overall efficiency of the system when those desiccants are integrated into the solution set.
Right. And those are actually like Amazon, I think I read, is deploying systems that involve those desiccants commercially now. Like those seems like pretty close.
That was an exciting news from 2 weeks ago. Yes, Amazon partnering with a startup, Transera, to deploy their product was really exciting to see.
And then there's solid state thermoelectric cooling. What the heck is that?
You mentioned one way of solid state cooling. There are more terms like that. There is a barocaloric and there is magnetocaloric, thermoelectric you mentioned. Basically, what solid state cooling is, that you use solid materials to produce the heating or the cooling effect by applying some kind of a force. That force can be a pressure, that could be a magnetic field, that could be an electric field. And when you do that with that solid material, it undergoes a phase change.
Right.
So the crystals in the solid, their alignment changes, And as a result of that, there is a phase change that happens, and you can generate heating and cooling. And this is a very exciting area of innovation where a lot of startups are working on all these kinds of caloric solutions, barocaloric, magnetocaloric, thermoelectric solutions. A lot of good activity and a lot of potential also, because of two reasons. You don't need a compressor because you don't have a refrigerant gas.
Right.
And that's what makes it really exciting and compelling in the context of the current refrigerant transition that we are in.
Right, because we still don't have that perfect refrigerant. So you
Yes.
eliminate refrigerants, you eliminate the compressor, which is the vast bulk of the electricity demand, right?
Yeah.
And so are those installed anywhere, or are they still, is this all lab and prototype stuff?
I don't know about the commercial installation, but I know that one company, which is again supported by RMI's third derivative called Magnotherm, which is from Germany, they have developed a beverage cooler or a wine cooler using magnetocaloric technology.
Where you're applying a magnetic field to this
Yes.
solid material.
Yes.
It's wild.
It's
And I'm assuming that similarly to solid state batteries, it's just a lot less maintenance because you have a chunk of solid material. You don't have as many moving parts.
I will say it's early to comment on that because of the nascent nature of these technologies, because you still need pumps and mechanisms to move the fluid. Material can produce the heat and the cool, but then you have to move that heat and cool to wherever you need it. And so you still need some of those pieces and the parts of heat exchanger and the valves and the pumps and the fan to ultimately deliver that cooling. So I will say there is much more to be learned and discovered about these from an overall maintenance standpoint as these units start to get into the field in the coming future.
I'm curious if about your kind of long-term view about the sort of relative effort and hope we should be putting into improving vapor compression units, like we've been talking about for most of our time, versus improving and scaling up some of these very promising alternatives. Like, which do you kind of place more hope in the midterm and long term?
Dave, I will answer that question slightly differently because I think we should be really looking at better cooling and whatever it takes to deliver that better cooling. And so, if urban heat mitigation measures are required to address the needs of a certain aspect and of the society and community, those solutions really need to happen at the right scale, and all efforts need to happen to build that resilience and mitigate that urban heat. Wherever there is new construction happening, let's make sure that our buildings are designed in a way that reduce that heat trap inside the building, so that we can reduce the need for that mechanical cooling in the first place, and again deliver better cooling, to people inside the spaces. And then yes, we have to do everything we can to avoid locking inefficiencies in our systems and making our grids stress during the hottest days by significantly improving the efficiency of the products, because it's not about stopping people from buying air conditioners. I mean, when people cross a certain threshold, they will buy an air conditioner. So then we have to think about how do you make it more efficient. And so in that context, I will say that in the short to medium term, there is a huge opportunity and a lot of effort should be put towards improving the existing vapor compression technology, because the entire ecosystem is designed around it, from an industry awareness standpoint, from a consumer awareness standpoint, from a policy and standards standpoint. And we should put all our heads and minds to solve that problem of how do we get vapor compression technology to its ceiling, and not just focus on raising the floor, but how can we really start pushing the overall efficiency of the air conditioners towards that ceiling that we have demonstrated through the projects like Global Cooling Prize. And in parallel, we have to start thinking about what application requires what kind of cooling. Do we need vapor compression based technology everywhere? Or for a product like a wine cooler or a vending machine, which is just sitting in a shopping mall in a corner,
Right.
can we use a more novel and sophisticated technology? And really, we need venture capital partners. We need innovators, we need adopters to come together to support these upcoming technologies so that we can start creating a market for these solutions as well, because we do need a buckshot of solutions, not just one silver bullet of solutions.
Right. And you don't worry at all that sort of like the traditional vapor compression kind of dominating the standards development and all that kind of stuff. You're not worried about that process kind of boxing out new disruptive entrants. Like you think these can peacefully live together and proceed alongside one another.
It's a very interesting question. I think there is an opportunity to build partnerships here.
Mm.
Because while the industry is doing its part of, again, pushing the ceiling through, we are helping them to kind of continue to do that. They're doing that. They're also looking out for other opportunities. And let's be honest, industry has the scale.
Mm-hmm.
Industry has the capability to test products. Industry has the capability and the network and the voice to get the products certified. And so I say that startups should really think about how can they collaborate and partner with these manufacturers and create value for the community and for the ecosystem, because they will need each other to ultimately solve the cooling problem and scale these exciting innovative products that are needed to solve the access to cooling issue.
Okay. Final question, which is just I'll ask you to speculate a little bit, look down the road a little bit. You know, that if you listen to these IEA projections, you know, you just look at sort of the current trajectory, it's pretty dire. It's pretty dire, you know, because obviously this is not, I mean, maybe I should have emphasized this more at the beginning, but this is not about luxury, right? Or like, this is about survival for a lot of people. The earth is getting hotter. No one involved in any of this wants to deny the best cooling technology to people who are going to be living in these hot and humid environments that are coming. So this is not something we can not do. But if you look at the projections of like the impacts of doing it, it's pretty dire. It's going to, you know, be an enormous chunk of global greenhouse gases. So I wonder, are you bullish on progress here? Do you think those projections are going to be overstated? Do you think we're going to manage to pull this off and to hit that ceiling and to reduce the need? And sort of what do you worry about in terms of kind of blockers or problems? Like what's the naughtiest part of this problem to you, and how optimistic are you about getting through it?
I do think that we have all the solutions that we need to bend the curve. We have good understanding of what it takes to mitigate urban heat. We have solutions for that. We have solutions that can reduce the heat trapped inside the buildings or preventing heat gains inside the buildings through passive measures. We have solutions for that. And we know what it will take for others to adopt it also. And then we know from a technology standpoint what solutions can again bend the curve from an energy and emissions and peak demand standpoint. So I actually agree with you that it should not be treated as a luxury anymore. Cooling access is critical for health and safety. The goal is also not about less cooling, and or we have to suppress the cooling demand. I think what's really needed is we have to deliver better cooling. Where people need more access to cooling, we have to make and find ways to deliver better access to cooling. Where we can avoid the waste, where we have to avoid that waste in all forms, whether it's refrigerants, whether it's electricity consumption. And we have to ensure that air conditioners and any aspect of the cooling technology and to cooling solutions can really support the power systems that often get stressed during the hottest parts. And to the second part of your question, which is the naughtiest part.
Yeah, what keeps you awake at night?
Yes. What keeps me awake at night is when I see the projections of cooling electricity consumption tripling from 5,000 terawatt hours, which is the same as what US consumes today entirely, to 18,000 terawatt hours by 2050,
Yeesh.
which is the entire electricity consumption of US, China, India, Japan, and Germany. So, five major economies of the world. That keeps me awake. At the same time, the potential that we have demonstrated that RMI through its Global Cooling Prize initiative and the Global Cooling Efficiency Accelerator initiative, we have demonstrated what's possible. That keeps me hopeful, motivated, and also awake that we can solve this problem.
Awesome. Well, that sounds like a great place to wrap up. Ankit, thank you so much. This has been just extraordinarily illuminating. I appreciate it.
Thanks, Dave. It was great to chat with you.
Thank you for listening to Volts. It takes a village to make this podcast work. Shout out especially to my super producer, Kyle McDonald, who makes me and my guests sound smart every week. And it is all supported entirely by listeners like you. So if you value conversations like this, please consider joining our community of paid subscribers at volts.wtf, or leaving a nice review, or telling a friend about Volts, or all three. Thanks so much, and I'll see you next time.